So this is the first very good, lecture class for the Kinematics Momentum chapter, which is the second worksheet of our syllabus. Contents of this chapters are actually quite simple. Much of the stuff should be derived from our O-levels study. So we'll have a quick recap of the stuffs that we have, which are brought down from the O-levels, and we'll also discuss the new things as well. Just to begin with, the basic definitions: distance, displacement, speed, velocity, acceleration, force, the way we handle the time graphs, displacement time graphs, velocity time graphs, and we can also have some other graphs, not essentially with time related, but some other graphs can be also involved for our processes. The key new thing for this chapter is the basic concept of momentum. How does momentum happen, and why? How does it help to do certain calculation? Momentum was a topic which was, I think, deliberately skipped from the O-levels discussion. I don't know why. Let's say people feel it that way, that momentum is not to be introduced in the O-levels syllabus for some reason. However, momentum is a pretty interesting concept, can help to handle a lot of stuffs. There is a video that I posted a couple of years ago, a couple of months ago, about the definition of momentum. Definition of momentum itself can have a lot of different variety depending upon how you are looking at the physics of the irrelevant stuffs. It's pretty interesting and to somewhat difficult as well. So let's get on with the topic. The first thing that we have are the definitions, which I just said. I'm not going to talk about the definitions in detail. I consider that you remember these stuffs. The second thing that is very important for you to remember is the vector geometry. Vector geometry means you have to understand / recall the ideas of triangle rule and the parallelogram rule. Parallelogram rule. Now, there's a new thing that we have over here for vector geometry, which we call the Polygon Rule, which is the third rule that we have, Polygon Rule. Polygon Rule is basically an extension of the triangle rule. So I'm going to write it that way. It's an extension of the triangle rule. I want to say how what this is. One of the primary things that we need to understand for the triangle rule is that goes like this: that if we have a vector equation that looks like this, let's say vector x plus vector y equals to vector z, the way that the triangle rule should work, that we should, with scale and direction, draw the vectors x and y one after another in the way that the figure has them, and then the computing side of the triangle, let's say this is the computing side of the triangle, would give us the resultant. As for parallelogram rule, it says that we should place the two vectors starting from the same point. Let's say x is going to work in this way and y is going to still start from the same exact point, and we are going to have these two vectors starting from the same point. We have to complete the parallelogram by drawing parallel lines on both sides, and the diagonal of this parallelogram should give us a resultant. These are two very basic examples that we have seen in our earlier classes. We're going to see some additional formula for the parallelogram just after a while. But before that, let me discuss a bit about the polygon rule. The idea of polygon rule is very simple. If in any case there is a situation where multiple different vectors, more than two vectors, result up to a resultant, then we can take help of the polygon rule. The idea of polygon rule is this: that if you have a situation, let's say vector a plus vector b plus vector c plus vector d, together they make the resultant vector r. If you have a situation like this, how can you find out the resultant vector r in graphical method? Easiest. One of the simple example that I can put is, let's say we have an object over here which is subjected by multiple four different forces. Let's say a force is, let's say 10 Newton working this way, b force is let's say 15 Newton working that way, c force is, let's say 12 Newton working that way, and maybe d force is working this way. which is, let's say, 25 Newton. I'm just assuming these numbers. And for the sake of your math working, you would be provided with all the relevant angles that you're going to need. For example, let's say this is how much? Let's say 60 degree. Let's say this is 90 degree. And here we have already 150. So let's say this is 110 degree. So 150 plus 110 gives you 270 degrees, I think, 270 degrees. So the remaining is up over here, whatever that is from the 360 degree calculation. Now you can very easily place these 4 vectors in a polygon, one after another, in the same way triangle rule works. So how can we do that? If we take for the scale, you should understand that in the scale diagram, 10 Newton is the smallest of the forces, 12 Newton should be slightly bigger, 50 Newton is bigger than 12 Newton, and 25 Newton should be nearly double of the 12 Newton force. So if you take the appropriate scale and start to place all the vector forces, one after another. So try to understand that. Let's say we start from this point, we place the A vector by how much divisions should I take? 10 Newton. So maybe I will take 5 divisions over here. So let's say 5 divisions in this direction, representing force A. Then B vector should have a 60-degree angle with the A vector. So this is the possible direction, that this is the ongoing direction for vector A. So we can draw up a 60-degree angle over here using our protractor. And then along this line, we should draw a 50 Newton force, which should be, in this case, I took 1 division for 2. So this should be 7.5 division long. So 2, 4, 6, 7.5. If I take about an arc of this much length, about this much. About. So let's say this is our vector B. Then from this point, this is the direction for vector B. So this would be the direction for vector B. With this vector B direction, you have to draw the C. So you can place your protractor over here, get a 90-degree angle right over here with your protractor. And your C vector should be in this direction with a value of 12 Newton. Let's say it goes up to here. That is representing to 12 Newton. I'm assuming these numbers. And then the D vector, which is about 25 Newton, should be represented by 12.5 divisions for my scale figure over here. This is about 90 degree. This is 60 degree. This is force A, force B, force C. And as for the D vector, we have to start from here. And with this alignment of C, we have to measure up. Let me use a different color. Or maybe I can take the equation further out. Hold up. Can I select everything here? No, I cannot.
Sir, it's C, sir. I mean, which one is C?
The upward left.
Okay, sir. And sir, can you increase the thickness of your, I mean, the thickness of the lines and everything?
Sure, I can. So let's say this is our this was our C vector. So this C vector finishes here. And now I would like to draw the D vector with a 110 degree with the alignment of the C. So you can place your protractor over here, measure up 110 degrees. Let's say this is 110 degrees. And then you can draw up the D vector like that. Let's say in this case, the D vector does not perfectly match onto the starting point of the A vector. So this is your D vector. So it's very much similar how the triangle rule works. You have a look at the triangle rule. The way triangle rule works is that you place the component vectors. Component vectors are the vectors which make up the resultant. So resultant is the vector, which is the final output. And component vectors are the individual parts which make up the resultant vector. So if you place the component vectors one after another with appropriate scale and direction, then the completing side of the triangle gives you the resultant. So for the polygon rule, the idea is very simple. You have to place all the component vectors one after another with appropriate scale and direction. And then the completing side of the polygon gives you the resultant. So in this case, let's say D, if D is extended up to this much, let's say in that case, the resultant would be given from the end point of D towards, this would be our resultant. And the direction of resultant should be reverse compared to the component direction. So in this case, you can see that the components have their direction aligned in a sort of anti-clockwise rotational direction. So the resultant should be working this way, pretty much like the triangle rule. Like you see that the resultant for the triangle rule started from the first vector and finished up at the end point of the last vector. same thing. So here the resultant is going to be working. This is our R. It's going to start from the first point of the first vector, and it's going to finish at the end point of the last drawn vector. So this is what we call a polygon rule, and this is possible to, this is helpful in a lot of different scenarios. One of the useful things that you have to understand that if in any case multiple vectors produce a resultant. So what do I mean by that? Abdul, just a second. If in any case, let's say if this was a scenario where I say that these four forces working on this object produces a equilibrium, or that would mean that the total resultant of these four forces should be 0. In that case, this should be a closed polygon. A closed polygon would mean that if it was 0, then all of these four sides should give us a completely closed polygon, which means the end point of the last vector will perfectly fall on the starting point of the first vector. The resultant value should be 0. If they do not produce a resultant 0, let's say if these things do not produce a resultant 0, so there is some numerical value of these four forces, then the end point of the last vector and the starting point of the first vector should not perfectly match at a given point. So you'd have to draw a last side of the polygon to complete that polygon, and that length and direction of the polygon should give you the resultant. So if the resultant is not supposed to exist, then your polygon should be a closed polygon. That's the term that we use. Closed polygon means where the polygon is basically a four-sided polygon which is perfectly closed, something like that. And if your resultant is non-zero, then you might actually have an open polygon. This is something that we call an open polygon. And to get the resultant, we just have to complete the polygon with appropriate direction. No, and that can give us the resultant like that. So these are the two terms that we'll be using pretty commonly: open polygon and closed polygon, for judging whether multiple different forces give us a 0 resultant or not. Abdullah, bolo.
Directionটা কিভাবে লিখবো স্যার রেজাল্টেন্ট ফোর্সে?
Oh, you can measure the direction from the figure if you need. For any case, you can actually measure how much angle is over here, and you can directly say that you can measure the length, and you can write the direction that resultant is working at this much angle with the a vector. That would be good enough. If you want to define it even further, if you want to specify it even further, you can say that the resultant is working with this much angle with the a vector. No, in this case, you can only say that much, because these four forces might be oriented in a different way. Only mentioning the angle with any of the component vector is good enough. You can either mention about this angle, or if you want, you could also measure up this angle, and you could also mention this with respect to d as well. That's your choice.
স্যার ডি এর অ্যাঙ্গেলটা কি এটা নিব নাকি ওই সাইডেরটা নিব, লাইক 180 থেকে সাবট্রাক্ট করে?
Now we always prefer to give obtuse angles, so angles which are preferably the small for the junctions.
Yes, sir.
For the answer that we prefer it that way, and that will more or less suffice. And to be honest, whenever two different vectors have an angle of, let's say, 120 degree, in vice versa scenario, we can also say that the angle between those two angles is also 60 degree as well, because those two things would make up. No, 60 degree to na মানে কি যেন বললাম, দুটো ভেক্টরের মাঝখানে অ্যাঙ্গেল যদি 120 ডিগ্রি হয়, in other words, you can always say that the angle between those two angles is also this much, which is কত যেন হবে দিলে 240. So vice versa আমরা এটা বলতে পারি. So mentioning this angle essentially means that you have two different lines which are producing this much angle. So the outside angle should be 360 minus that angle. So that is an implied information which you don't have to bother in any case. বুঝে গেছে?
স্যার
Yes, sir.
আচ্ছা, হ্যাঁ আব্দুল্লাহ বলো। মুনাম বলো।
স্যার আমি মনে আমাকে স্যার ওই যে রেজাল্টেন্টের ডিরেকশনটা অপোজিট কেন একটু বুঝতে পারতেছি না এটা।
কোনটা?
ওই তো রেজাল্টেন্ট আর কি আটটা মানে অপোজিট ডিরেকশন যে।
Yeah, that's the idea of triangle rule or polygon rule, that if you are trying to draw multiple forces one after another, the resultant is always obtained in the opposite sequence of the component vectors. So it means that the resultant will be aimed from the starting point of the first vector of your diagram towards the last point of your towards the end point of your last vector. That's how we get the resultant from triangle rule drawing.
আন্ডারস্টুড।
আচ্ছা, আমাদের প্যারালোগ্রাম রুল নিয়ে আমাদের কিছু নতুন ক্যালকুলেশন আছে, সেই নতুন ক্যালকুলেশন গুলো আমি তোমাদেরকে এখানে একটু দেখাই।
স্যার
হ্যাঁ বলো।
আমরা কি সবসময় এক্সটেরিয়র অ্যাঙ্গেল নিব পলিগন
ইউ প্রেফার,
ড্রয়িং?
আচ্ছা মানে এখানে যখন আঁকতেছিলাম আঁকার জন্য,
ইয়েস।
আচ্ছা আঁকার আইডিয়াটা হচ্ছে এরকম যে what you need to understand that the way these angles are given, try to understand this information. This is a good question. Whenever you are, if you have a look at this direction, vectors are quantities which depend upon magnitude and direction both, which means if you are trying to direct a certain vector in a certain direction, if you're trying to mention or draw in a certain direction, you have to consider in which direction it's working properly. Typically, one of the easiest way that can work for you while you are drawing a vector diagram is what I propose is that prefer to draw your vector diagram in the same direction it is given in the question. For example, in this case, A is given horizontally to the right, B is given horizontally upward right, C is given upward left, and D is given downward left. So if you try to stick up to that direction, most of your angles will work out. But how would you know that whether you should draw that angle inside or outside? That's a pretty interesting question. Here's the deal. Try to understand, for the sake of the purpose of this diagram, the way polygon rule works is that we have to place the vectors one after another, which means at the end point of vector A, we have to place vector B. You have to understand, although vector A finishes here, the direction of vector A is not finished here. The direction of vector A is practically a direction that can be used in any place. The direction of vector A is working this way. This could be here, this could be here, this could be here, this could be anywhere. In your whole considered plane, the A vector is working horizontally to the right. So B is directed, the direction of B vector is making 60-degree angle with the direction of A vector, not exclusively with A vector. Wherever A vector is, that's a different issue. But the angle that it is making is with the direction of A vector. So that's why I had to preferably draw the angle right over here, because this is the direction of A vector towards right. My A vector finished over here, and I had to start the B vector from this point, because that's how the drawing that's how the drawing works. That's how the polygon rule actually works. But
ইয়েস স্যার।
বুঝে গেছে আমার কথা?
ইয়েস স্যার।
Beautiful. বুঝলে ঠিক আছে। Any further question about this polygon rule stuff?
স্যার কোনটা কখন দিব স্যার, এটা কি বলা থাকবে স্যার কোশ্চেনে?
Well, ideally, it's pretty simple. Pretty simple মানে হচ্ছে যে যদি আমাদের basic দুইটা force থাকে, for example, if you have x plus y equals to z, we usually go for triangle rule because that essentially incorporates three sides of a geometric structure. But if you have more than two forces or more than two vectors resulting in a single vector, then we can go for the polygon rule. Polygon rule is basically, what can I say, an extension of the triangle rule. The reason I'm saying that is that it's not essential that you have to learn polygon rule. If you only know triangle rule, you can also work out multiple different forces. For example, you could very well do A plus B, you could get a resultant force, let's say that is P. And then C plus D, you could very well get a resultant force that is Q. Then you could find out the triangle rule for P and Q, and eventually you could get R as well. So you can take two of the available forces of the polygon one at a time and use triangle rule for those two, and then solve it for every pair, and then join the pairwise, and eventually you could get to the same result. Polygon rule basically saves you all the trouble of individual triangle rules and gives you the whole outcome in a single process. You don't have to essentially, I mean, this is basically a normal sense that if you have more than two vectors involved, we prefer to use the polygon rule because that usually lessens our effort. Yeah, Sadman bolo.
Sir, my question was, in polygon rule, which vector or force we will take consider first? ওইটা কি স্যার বলা থাকবে স্যার?
না, ওটা বলা থাকবে না. I could start this vector diagram with any of these four forces. It doesn't matter.
You can use anyone at any time, sir.
I could start my vector as any of the forces, but whenever I'm drawing, I have to make sure that the angles that I'm using are properly oriented. For example, for your question, let's say if I wanted to start this vector diagram with vector D, let's say, and after D I want to draw vector C, I could do that as well. I can try to draw this over here. Let's say vector D is working this way, somewhat of this direction of 25 Newton. So I have to draw a scale of this much with 25 Newton. And then I can see that with the direction of D vector is finishing here. So this is the direction of D vector. With the direction of D vector, C is supposed to work upward left at an angle of 110 degrees. So I have to place my protector over here. measure up 110° like that, which would be slightly bigger than 90°. So let's say maybe up to here. And I could draw the C vector right from this point, and it can go up like that, having a value of 12 Newton maybe, and this is 25 Newton, so this should be a bit longer. So this is 110°, and this is your C vector, this is a D vector. You could also start from your, you can start your vector diagrams from any of the forces. Your starting vectors would not be defined in most cases. That's your choice. So whatever is convenient for you to work with, you can choose as you want. Ultimately, your resultant force should be exactly same, provided your figure is drawn correctly. Bucho.
Yes, sir. And sir, so does the order of following which vector comes next, does that take into any importance?
I mean, you're asking that whether if we write this equation in any other form with plus sign in between, would that matter or not? That's your question.
No, sir. I mean, for example, instead of after A, instead of C, I just jump to B and then another one.
Yeah, you could do that. Yeah.
Oh,
Order doesn't matter. As long as the figure is drawn right, you would always end up with the same correct answer. Order does not matter. That's the answer to your question.
thank you, sir.
Sure. The next thing that we need to consider or observe is for a bit more additional calculation for the parallelogram rule. Do all of us do all of you remember how the cosine rule work?
Yes, sir.
Yes, sir.
Actually, just a quick recap for those of you who I believe most all of you know cosine and sine rule, but still I'm gonna just show you this thing pretty fast one time, because we're gonna need to use those rules in our calculation for the upcoming stuffs. So the idea of sine rule goes like this: if you have a triangle and the sides of the triangles are labeled, let's say the corners are labeled, let's say A, B, and capital C, and conveniently the side of the triangles are labeled by small letters, let's say small a, and I mean opposite side of angle A is small a side, and this is small b, and this is small c. In that case, sine rule gives us this, that A divided by sine A should be equals to B divided by sine B should be equals to C divided by sine C. This is the sine rule, which is pretty simple, and it's a convenient rule to use in a lot of different cases. We're going to see about its use after a while. The cosine rule, on the other hand, can have three different individual expressions. So one of the expressions for cosine rule can go like that. I mean, if I start with angle, I can write that cos A is given by b square plus c square minus a square divided by 2bc. Or if I just subject a square from here, because choosing the angle A means I'm trying to find out deal with the opposite side angle. So this could be also rewritten in this format: a square equals to b square plus c square minus 2bc cos A. This is usually the most common variation that you might have come across, other than this variation, because this is a linear expression. So can be more convenient to write in many cases other than this whole large fraction expression. So in the same way, you can write the all other parts as well. If I go for b square is going to be written as c square plus a square plus, sorry, not plus, minus 2ca into cos b, and c square written as a square plus b square minus 2ab cos c. So these are the three different expressions you might come across. For the parallelogram rule, what we're going to see that this minus sign would be somewhat logically converted into a plus sign. So let me show you what that means. Consider a scenario. Let's say we're going to draw consider a scenario that we're going to draw up a vector diagram for two vectors. This is P plus Q equals to R in a parallelogram rule, in a very simple parallelogram rule. So let's consider we have a horizontal force, horizontal vector P, and let's say Q is working this way. And let's say the angle between them is alpha. I could use theta as well. Should I use theta? Alpha. I'm going to use alpha anyway. No big deal. And I can complete the parallelogram rule right here. So this is my complete parallelogram. And if I draw this up, maybe with red, not the best of the figures, but this is our resultant for the parallelogram rule. Let's say this R resultant is producing an angle of theta with the p vector, because that's we have to define how the resultant vector works. So just from these four information, p, q, r, and alpha and theta, how can we find out the value of r by means of some formula other than doing the whole drawing for each individual problem we're gonna have? So we're gonna try to devise some generic expression for r and theta in terms of p, q, and alpha. Alpha would be given to us, p and q would be given to us. Our aim is to define r and theta for the upcoming process. So here comes some additional drawing. Let's say we extend this line a little bit and we draw a vertical from here, right on this line. This is a 90-degree. By logic, this should be also alpha. And if this is q side, the length of this side should also be q. So we can pretty much say that the length of this side can be written as q sine alpha, and the length of this much can be written as q cos alpha. এটুকু পর্যন্ত বোঝা গেছে কিনা?
স্যার এই ট্রায়াঙ্গেলটা বুঝিনি, ব্রু ট্রায়াঙ্গেলটা।
Oh, we extended the p side horizontally to the right, and we drew a vertical from this vertex onto the extension, so that there is a perfect 90-degree between them. So we get a right angle triangle over here. This blue part is the new additional drawing, and because this is an alpha angle, this will also be an alpha angle, because corresponding angle q and q side are what is parallel to each other, and in this case this horizontal side is the transversal. So alpha and alpha should be equal because they are corresponding angles. And then we applied some trigonometry that the adjacent side is given by the cosine ratio, and the opposite side is given by the sine ratio. Achha, for those of you who do not recall this expression, or you might not have come across this expression, that how did these two sides become like this, I'm going to set up this thing. I'm going to show you this expression, these two expressions over here with a different triangle. Maybe I'm going to draw the same triangle for you to understand. This is my my q looks like theta, so I'm sorry about that. So let's say this is a triangle. Oh, beautiful. It automatically becomes a triangle. So let's say we have an angle over here that is alpha, and this hypotenuse side is q. So let's say this side is the opposite side, and this is the adjacent side, and this is obviously q side, which is the hypotenuse. Now logic tells us that the ratio of sine alpha should be given by opposite by hypotenuse. So if I just cross multiply, I can write that opposite side can be expressed as q sine alpha. In the same way, the ratio of cosine alpha is given by adjacent side divided by the hypotenuse, which in this case is q. So if I just cross multiply, I can write that the adjacent side should be equals to q cos alpha. Now, what I'm trying to show you over here is basically these two expressions, that q sine alpha and q cos alpha. What you need to understand that whenever you have a right angle triangle in any given scenario, the side of the right angle triangle, I mean, one of the side of the right angle triangle is obviously the hypotenuse. Hypotenuse is basically hypotenuse. Between the other two sides, one of them is defined as the opposite side. One of the side is defined as the adjacent side, depending upon where we have considered our angle. So this is the angle that we have considered for this case. So one of the side of so the angle will be created by two sides. One side is always the hypotenuse. The other side that makes up the angle is what we call the adjacent side. So this is the side that is adjacent to this angle. That's why we call it adjacent side. And this is the side which is opposite to this angle. So that's what we call the opposite side. The opposite side of a right angle triangle is always expressed as q sine alpha. So basically it's called the sine ratio of the hypotenuse, and the adjacent side is given by the cosine ratio of the hypotenuse. So that's from where we actually wrote these two expressions for this drawing. বুঝা গেছে কিনা?
জি স্যার, বুঝতে পারছি এখন।
Beautiful. So if we now try to draw Pythagorean law for this large triangle, which I am going to try to label with the green, let's say this large triangle. So we try to apply Pythagorean triangle. Can I actually squash this? I cannot squash this, so I'm going to do Control Z. So if we apply Pythagorean rule for this triangle, I'm going to write r square equals to P plus Q cos alpha whole squared plus Q sine alpha whole squared. I want to start working on this. This is P squared plus 2 PQ cos alpha plus Q square cos square alpha.
স্যার
plus-
থিটা হবে না?
No.
The large green triangle তো theta একদম।
Yeah. I'm applying Pythagorean rule here, not the cosine rule. I'm applying Pythagoras.
Oh, okay.
So basically, I'm working with the lengths. R square equals to, I mean, this squared equals to this squared plus this squared. বুঝছো?
Yes, sir.
আচ্ছা। So এখান থেকে যদি আমি এখন q স্কয়ারটাকে কমন নিয়ে নেই তাহলে কি পাবো? p স্কয়ার plus q স্কয়ার into cos square alpha plus sin square alpha plus 2pq cos alpha. So ultimately you are getting r squared is given by p square plus q square plus 2pq cos alpha. So that's basically one of the expression for the hypotenuse. So you can pretty much get the resultant vector size or length magnitude, that is, if you know the value of p, q, and alpha from this expression. Or if I just want to get rid of the square, there will be root over sine over here, which makes it a bit more simpler. এখানে minus হয় নাই, minusটা কেন হয় নাই? That's what I'm trying to explain. This is very much similar to what we have seen for the cosine rule, but in the cosine rule, we have a minus sign over here, but here we do not have a minus sign. The reason we do not have a minus sign over here is like this. Try to understand. If you want to, I mean, this thing came from the a plus b whole square formula. That's why we don't have a minus sign. But how can we explain this in terms of that thing? I'm gonna label one specific triangle over here with this rainbow color pen. Try to have a look at this triangle. This side, and this side. Have a look at this triangle that I'm labeled with rainbow color. This one, and this one. Consider the fact that here we have alpha angle. So what should be this angle? What this angle should be?
Minus alpha.
No,
180 minus alpha.
180 minus alpha.
Sorry.
it's okay. This angle should be 180 minus alpha. So from this triangle, if I want to apply the cosine rule using this angle, so in that case, R would be the opposite side. I'm going to try to write that in that format. Have a look. R square equals to p square plus q square minus, this is the minus sign for the cosine rule, minus p2 pq cos of 180 minus alpha. ঠিক না? এখন cos 180 minus alpha value কত? এইটুকুর ভ্যালু কি?
minus cos alpha.
এইটুকুর ভ্যালু হচ্ছে minus cos alpha, which means ultimately what you're gonna get p square plus q square plus 2pq cos alpha. বুঝতেছো কেন এই জিনিসটা প্লাস হয়ে গেছে? Because
Yes,
the
sir.
angle that we're handling is no longer alpha for that specific triangle. It has become 180 minus alpha because alpha has gone outside the parallelogram. Because it is 180 minus alpha, and cos 180 minus alpha gives you minus cos, so that those two minus signs multiplied to each other ultimately results in a positive sign. বুঝা গেছে কিনা?
জি স্যার বুঝে গেছে স্যার।
আমি তোমাদেরকে প্রথমে cosine rule দেখালাম. First I showed you the cosine rule, then I showed you the derivation of this whole thing using Pythagoras. So it's a different way of derivation, so it should be correct. Then I showed you that how did this minus sign actually became plus using the cosine rule. Once again, it's because of the angle. That's the total information for this thing. So by this method, we can find out the value of R. We can find out the magnitude of the resultant. How can we find out the value of this angle theta? Finding out the value of theta can prove to be pretty simple. Have a look over here. Once again, if we go for the large green right angle triangle over here, this is the theta over here, where this side is given by q sine theta, q sine alpha, where this side is p plus q cos alpha. So I can pretty much write that tan theta can be given by the opposite by adjacent. So that is q sine alpha divided by p plus q cos alpha. That's basically the expression for the resultant's angle. You can pretty much subject theta from here. Theta equals to tan inverse that value. So that can give you the whole expression. If I now, so the key two equations that we are trying to get out of this whole discussion, one is this red rectangle, and the other one is this one. So the idea is that if we are provided three information, let's say we are provided the information of P, how big is P, we are provided the information of Q, how big is Q, and we are also provided the angle alpha. In this case, the angle alpha was defined as the angle which is the angle between resultant and P vector. So alpha was defined as the angle. So P was the vector with which alpha was, sorry, I'm bhul likhchi, P and Q, and alpha is given where alpha is the angle between the P and Q. So they are working with this much angle. So 18 information তোমাকে দেওয়া আছে, 18 information থেকে তুমি বের করতে যাচ্ছ রেজাল্টেন্টের ম্যাগনিটিউড কত হবে এবং রেজাল্টেন্ট কোন ডিরেকশনে থাকবে. So we are assuming that the direction of the resultant is theta, where we have considered that theta is the angle between the resultant and between the P vector. So that is important কারণ otherwise আমাদের এই দুটো পজিশন নিয়ে আমাদের জাজ করতে হবে. So if that's the scenario, the way we can write this is that the resultant can be given by root over of P square plus Q square plus 2PQ cos alpha. That's the magnitude equation, and theta can be given by tan inverse, because P is the adjacent side, P goes at the bottom, P plus Q cos alpha আর উপরে হচ্ছে Q sin alpha. So এই এক্সপ্রেশন থেকে আমরা খুব ইজিলি এই তিনটে ইনফরমেশন গিভেন থাকলে আমরা এই দুটো ইনফরমেশন বাই করতে পারি. এটুকু হচ্ছে এই পার্টটুকুর ডিসকাশনের আউটকাম. These you might feel like that এগুলো আমাদের জানা লাগবে কেন, এগুলো তো সরাসরি আমাদের ফিগার থাকলে আমরা সরাসরি বাই করতে পারি. হ্যাঁ, আমরা সরাসরি বাই করতে পারি, কোনো সমস্যা নাই. If it's required, we can draw up a necessary trigonometric drawing, and then we can draw. Hello.
Hello.
বলুন, কথা শোনা যাচ্ছে? আচ্ছা, মাঝখানে আমার একটুখানি আইপিএস একটু জাম্প করছিল. I don't have a functional IPS, but it does all the typical problem of the IPS. Anyway, IPS ঠিক করে দিয়েছি, IPS hopefully ঠিক হয়ে আসবে. Point is that we can if you don't want to if you don't want to use these equations, you can essentially draw up a triangle or draw up a parallelogram and work your way through the very basic process of how the trigonometry and geometry works. That's not a big deal, but that can prove to be time consuming. In your paper 2 exam, you have 1 hour 15 minutes. In your paper 1 exam, you still have 1 hour 15 minutes. So time is something which is not a very much expendable resource. So you got to be careful while you are spending your time, because that's pretty important in my opinion. The next thing that we're going to see for today's class is what is the other thing? I went to the diagram, definitions, vector diagram. Okay, vector. Yes.
একটা কোশ্চেন স্যার।
Hello.
স্যার আপনি যে প্যারালোগ্রামের স্যার গ্রিন কালার যে যেটা দেখছেন স্যার, আর পাশে যে রেইনবো কালার দিয়ে যেটা দেখলেন স্যার, ওটা মানে স্যার ডিফারেন্সটা কি স্যার? বুঝলাম না
কোনটা?
গ্রিন কালার আর স্যার রেইনবো কালারটা।
Oh, the difference, there is practically no difference. I derived the green color definition using Pythagorean rule using the large right angle triangle, whereas I drew the rainbow color equation using the obtuse triangle, which is inside the parallelogram. They both ultimately end up with the same expression because the angle is different for these two things. I just showed you that the equation is valid even by cosine rule. It has a very much shape where that is very similar to cosine rule, but it has a plus sign. I tried to show you why that plus sign is there by actually showing it, deriving the formula from the obtuse triangle by cosine rule.
ওকে স্যার, থ্যাংক ইউ স্যার।
Sure.
স্যার রেড কালার যেটা কি লিখেছেন ওটা বুঝিনি স্যার, এই যে পি কিউ।
This one.
Yes sir.
Oh, this is a way to express that if there is a certain angle, which angle are we talking about? For example, in this case, this was alpha. Alpha was the angle that is between P and Q vector. So P,
Yes sir.
a vertical angle sine Q vector, and theta was the angle that we were trying to find out, where theta was the angle between resultant and P. Between these two vectors, theta was defined. This is a way that by which we can easily define angles.
Okay sir.
Sure.
ডেরিভেশন কি জানা লাগবে?
ডেরিভেশন জানা লাগবে না, ফর মোস্ট পারপাস তোমার ডেরিভেশন জানা লাগবে না, জাস্ট ইকুয়েশনটা মনে রাখতে পারলেই হবে। তোমরা যেহেতু কোসাইন রুল অলরেডি জানো, সো ইকুয়েশন মনে রাখতে ওটা ডিফিকাল্ট হওয়ার কথা না, জাস্ট মনে রাখলে হবে যে এখানে প্লাস সাইন হবে, দ্যাটস গুড এনাফ। আর এই অ্যাঙ্গেলের এক্সপ্রেশনটুকু একটু মনে রাখতে পারলে ভালো হয়, মনে রাখতে না পারলেও সমস্যা নেই, কারণ হচ্ছে ইফ ইউ ক্যান ফাইন্ড আউট দ্য ভ্যালু অফ আর or if you have the values of p and q, then you can directly go by another cosine rule to find out the value of theta as well. Finding out theta is not a big deal. You don't have to find out this theta angle using exclusively this formula, but if you want, you can.
Yes, sir.
Okay. The next thing we're going to discuss is what we call equations of motion. We have seen equations of motions in our O levels. There different teacher consider different number of equations of motions. I usually prefer to teach them by 4 equations which involve 5 variables. So the equation goes like this. The first one is v equals to u plus a t. The second one goes like s equals to u plus v divided by 2 into t. The third one is s equals to u t plus half a t squared. And the fourth one be v square equals to u square plus twice as. The first information that is important, that for this 4 equation of motion to be applicable, we always have to make sure that acceleration for the considered duration is a constant. Acceleration must be a constant for this equation to be valid. If acceleration is varied, then this will not work. So these equations will not work for a circular motion, because within the circular motion, even if for a uniform circular motion, the magnitude of acceleration remains the same, the direction of acceleration continuously changes, because centripetal acceleration always works towards the center. So you cannot consider these scenarios for a varied acceleration case. They are exclusively applicable for scenarios where acceleration is constant. Can be exactly constant, can be practically constant, but constant. One of the things that is important for us to understand, that all of these things actually can be they are vector quantities. In this case, velocity is a vector, final velocity is a vector, initial velocity is a vector, displacement is a vector, acceleration is also a vector. The only thing that is not a vector is time. So all of these 4 equations can be considered to be some sort of a vector expression, except for maybe number 2. What I'm saying is that v equals to u plus at, you can pretty much show it in a format like this. Let's say in a certain given scenario, if your u vector work in this way and your acceleration multiplied by time vector works in this way, let's say this is your a into t, then the velocity vector, final velocity vector, can be drawn very much like this, in the other way around, like that. I have a reason to show you this figure. What I'm trying to show you is that these 3 vectors, velocity, final velocity, initial velocity, or acceleration, can have individually different direction. There is no hard and fast rule that that force or the acceleration must work in the same direction as the initial velocity or in the direction of final velocity. Acceleration of an object or force working on an object is independent of the velocity. An object could be moving in any direction with any velocity. You could apply any force in any direction on that object, and ultimately what would be defined by that application of force is the final velocity. So all of these 3 things can have different directions. Don't get the wrong concept that you must have the force applied. I mean, even for those who are wondering where is the force coming from, we don't have any force over here. Force is coming from this equation, F equals to ma. Try to understand this thing. This is a vector equation, F equals to ma. M is a scalar quantity, which means this is basically a numerical multiplier of a. So if let's say if m is 3 kg, then I can say numerically acceleration times 3 gives you the value of force. That's what I'm trying to mean. Which means, because this equation is a valid equation, this essentially dictates that in any case, the force applied on an object and the acceleration experienced by that object should always work in the same direction. Force and acceleration must always have the same direction, because they are related by this formula where there is only a multiplying factor. But final velocity, initial velocity, acceleration, they don't need to have individually same direction. They might have same direction. I mean, for example, if it so happens that this was the initial velocity of an object and the force was working in the same direction, so you have this is the at of this object. You can also have that an object was going in the right direction, forces are also applied in the right direction, and then the object speed up. So this whole thing is currently your this whole thing is basically your final velocity P vector. That's possible. But it doesn't have to be. That's my point. বুঝা গেছে কি বলছি? বলবান?
স্যার
হ্যাঁ বলো।
স্যার একটা ইকুয়েশন যদি দুইটা ভেক্টর কোয়ান্টিটি থাকে তো
I'll help you finish your question. একটা ইকুয়েশন যদি মাল্টিপল ভেক্টর কোয়ান্টিটিস থাকে, ইকুয়েশনে যে কোনো এক পাশে যদি প্লাস অর মাইনাস সাইন থাকে, it would mean that the side which is singular is obtained from some sort of vector geometry out of those components. For example, this one and these ones. ঠিক আছে? But একটা certain vector equation এ যদি এরকম ফরম্যাট থাকে, for example, a equals to bc or y equals to mx. If it so happens that one of these vectors is one of these components of the two multiplied is a scalar quantity, then these two vectors must have the same direction. Because this is an equation, it means it has to be equal on both sides. If this vector has a direction in some direction, this vector cannot have a different direction because the directions are supposed to be equal on both sides of the equation in actual case of drawing as well. That's the whole idea of an equation. So you have to have same direction on both sides. But if it so happens that both of these quantities are different vectors, for example, let's say moment equals to force multiplied by distance from the pivot point. You might wonder, distance from the pivot point is a distance. Why do I give a angle? Because it's actually not a perfect vector quantity that we define. It's some sort of a tensor. Tensor is not taught in your syllabus. It's a bit complicated thing. Even for me, it's complicated. So, but what I'm trying to, acha, moment bad though. Forget about moment. If you want to define work done is acha, moment equation actually lektam. So, it am lag back to what I'm doing. Let's say if you consider work done is given by what? Force multiplied by distance moved in the direction of force. So that's actually vector quantity. It says in the direction of force. So these two vector quantities given multiplied gives you a scalar quantity. This is a very specific type of multiplication that you call dot multiplication or scalar multiplication. Whereas this one is what we call a vector multiplication, where multiplication of two different vector quantities gives you another vector quantity. Moment is a vector quantity, which is direction, anti-clockwise or clockwise. So this can happen for vector quantities. But if it so happens that in any case a certain vector quantity is obtained by a scalar quantity multiplied by a vector quantity, then these two direction must be always same. See if that answers your question that you had in your mind. Does it help?
Sir, is the vector and scalar multiplication signs are different, like the dot and the cross?
Yes.
Oh, sir.
বুঝা গেছে?
জি স্যার
তুমি যেটা জিজ্ঞেস করতে চাইছিলে সেটা আনসার পাইছো?
জি স্যার ওটা বুঝতে পারছি।
Beautiful. So similarly আমরা এই ইকুয়েশন এক মিনিট similarly আমরা এই ইকুয়েশন নিয়ে কাজ করতে পারি. For example, this is displacement equals to ut plus half it square. So this is also equally applicable for graphs as a for especially for graph. This is actually pretty important. Let me show you an example. Let's say a certain objects velocity versus time graph, VT graph, looks like this. Okay, that's the velocity time graph for an object given. You are asked to find out what is the distance covered by this object. I'm going to write this. In A, you're asked to find out what is the distance covered by the object. In B, you're asked to calculate what is the displacement of the object. How do you approach this problem? You have the necessary scales over here, not a bare graph like the way I've drawn. You have the velocity scale on both the positive and negative side. You have also the time scale given over here. How do you approach this problem? What's the difference between these two terms? Distance is the scalar quantity.
When it comes to
Like,
distance,
add
we'll add everything, and when it comes to displacement, the part of the graph which is in the negative side, we will subtract.
Beautiful. So if you are trying to find out the distance, let's say you find out all the individual areas that is under the graph. The graph finishes over here. So to find out the completing part, I might as well prefer to draw a right angle triangle over here. So let's say we have three different areas over here. Let's say this is the area of X, this is the area of Y, this is the area of Z. If you're trying to find out the distance covered by the object, you simply have to add all of these numbers. area of x plus area of y plus area of z. That's the total distance covered, how much path was traveled by the object. But if you're trying to find out the displacement of the object, you have to consider that this is the part of the vector, this is the part of the graph which has a positive velocity. This is a part of the graph which has negative velocity, which means for this part the object was moving in one direction, let's say right. For this part the object was moving in the opposite direction, let's say in this case this would be to the left, which means the displacement should be measured or should be calculated in accordance of how the value of v is changing. So for distance you simply have to add all the areas, x plus y plus z gives you the distance. But for displacement this should be x minus y plus z. All the positive side displacement comes on the addition side, and the negative side displacement comes on the subtraction side. Does it make sense? এই পার্টটা কি বোঝা যাচ্ছে?
Yes.
The same thing can be applicable for a lot of other cases, especially for oscillation scenario. For example, if an object is undergoing some sort of vibration or oscillation, in many cases we actually show the objects, let's say VT graph or maybe DT graph also in a fashion like this. The whole point of calling the motion an oscillation is that the object basically doesn't move away from its equilibrium position. It keeps on vibrating about its equilibrium position, and that's why it actually happens that way. And after any full multiple of time period amount, that total amount of displacement of the object would be 0, because after every time period it comes back to the same position. But if you want to calculate the distance covered by the object for a certain duration after a certain duration of time, you can always come up to a certain value. Distance covered would be the addition of the areas on both sides, whereas displacement should be the addition of the top sides, subtraction of the bottom sides. So that is a very important factor you have to consider, and you have to see very carefully on the axis that does this variable v, was it defined as speed in the quotient, or was this variable was defined as velocity in the quotient? If it is defined as velocity, you have to understand this is a vector diagram. Positive direction, negative directions are defined. If it was defined as a speed variable, then this would not actually matter. To be honest, if the diagram says it's a speed versus time graph, this graph, speed versus time graph, should never even exist on the negative side, because speed cannot be negative. An object speed can be only positive, because speed is only a scalar quantity. So if I want this graph, which belongs, some part of this graph belongs on the negative y-axis, is definitely a velocity time graph. If I want to convert this thing into a speed time graph, this is how the graph should look. So this part remains the same. This part simply gets reflected back on the positive side. This would be a speed time graph. Speed time graph cannot even exist on the negative side, because it simply doesn't have except negative values. The lowest value of a scalar quantity, absolute scalar quantity, can be 0. Difference of scalar quantities can be negative, but the absolute lowest value of a scalar quantity can be only 0. বুঝা যাচ্ছে কিনা?
জি ভাইয়া।
আচ্ছা, এখান থেকে আর ফার্দার কোনো কিছু খুব একটা কিছু বলার নাই। এই কোশ্চেন গুলো আমরা প্রপারলি ইউজ করব, এইগুলো আমাদের খুব কমনলি কাজে আসবে এবং খুব ইম্পর্টেন্টলি কাজে আসবে। ডিরেকশন ইজ ভেরি ইম্পর্টেন্ট, দ্যাটস দ্য পার্ট দ্যাট আই ওয়ান্টেড টু এমফাসাইজ ওভার হিয়ার। আর ডিরেকশন রিলেটেড ক্যালকুলেশন আমাদের সামনে কাজে আসবে। The next thing that I want to discuss is that I'm gonna jump into the discussion for the projectile motion. So projectile motion. Before I move into the actual concept of the projectile motion, I would like to tell you some very specific stuff. I'll take a break. I'll take a 5 minutes break. I'll be right back after about 5 minutes. Before I jump into the whole basic concept of projectile, I would like to help you remember. I would like to give you a little bit of concept for what we are trying to do over here. What would be our end goal? First thing is this: if we ever have a vector quantity, let's say whatever that vector quantity is, let's say a vector quantity is given as r, we can always divide that vector quantity into two vertical components. So let's say one component is like this and the other component is like this, in such a way that there would exist an anti-degree between them. We call this the horizontal component. Let me show this as Rx. This one is represented as the vertical component, shown as Ry. If the angle over here is, let's say, theta, then the individual values of Rx and Ry can be obtained. The value of Ry will be R sine theta, which I showed you a bit earlier, and Rx value would be R cos theta. This vector diagram dictates that R vector is such a thing that we have divided this into two vector components in such a way that R vector can be obtained as the vector sum of Rx plus Ry. That's the idea of triangle rule. So what is important is that if we have the R vector, we can calculate this. So from the vector quantity, we can find out the components. This is possible to achieve. Vice versa, if it so happens that for a certain vector quantity, let's say, once again, let me use a different number, let's say x. Let's say we want to find out this vector quantity, and we want to find out this vector quantity. Finding out the vector quantity means finding out its magnitude, also finding out its direction. In any case, if we want to find out a certain vector quantity, another approach can be that we can somehow, by mathematical or graphical method, we can somehow calculate, other than writing this as x, maybe I can write this as a different number, because I'm going to use the x as the horizontal direction. Sorry for the jumping factor. So choosing the eraser, let's say a certain vector is p. Let's say there is a vector quantity that is p, and we want to find out the p vector. So we want to find out the direction and magnitude of this vector p. Another logical way is that somehow graphically or mathematically we can calculate the horizontal component of p, and then we can calculate the vertical component of p. And logic tells us that the magnitude of p should be equals to px squared plus py squared root over. If you wonder where this is coming from, this is coming from Pythagoras. Actually, I should have written p square equals to px squared plus py squared. I did not write the square over here, so give the root over here. So this is somehow, so if you can find out these two values, you can find out the magnitude of the resultant vector. And if you know the value of these two vectors, you can also find out the angle, let's say tan theta, by the ratio of these two vectors, from where you can find out the theta as well. Theta would be given by tan inverse vertical component divided by horizontal component. This can also work. What am I trying to show you over here? I'm trying to show you two different interchangeable conversion. If we have a certain vector quantity available to us along with the angle, we can find out the components. If we have the components available to us, we can find out that vector quantity. এই জিনিসটা বুঝা গেছে কিনা?
স্যার আবার রিপিট করবেন কথাটা কি বললেন?
If we have the certain vector quantity available to us that is given from the question along with the angle information, we can find out the two components, vertical components and horizontal components. We can find out those numbers. Vice versa, if we have the component values of a certain vector, we can find out that vector quantity also.
Yes, sir.
ঠিক আছে, এই জিনিসটা আমাদের কাজে লাগবে, কিছুক্ষণ পরে কাজে লাগবে, সো আমরা জিনিসটা দেখবো। Projectile motion. So how do we define a projectile in normal sense? A projectile is basically an object which is thrown. Any object that is thrown can be said to be a projectile. However, for our syllabus, the projectile is defined for a very specific type of motion. For our syllabus, projectile is defined as long as it is moving only under the effect of gravity. I'll say it again. The projectile motion is defined, or a thrown object or a moving object is only defined as a projectile as long as it is exclusively moving under the effect of gravity, which means for the sake of simpler calculation, we're going to consider any other force other than gravity to be non-existent in our scenario. So air resistance will not be a part of our calculation. Any type of other fluid resistance will not be part of our calculation. projectile motion will be considered to be projectile motion as long as the object leaves from the throwing mechanism. So let me give you an example. Let's say this is ground, this is me, and we are not drawn to scale. In my hand, I have a piece of rock that I'm about to throw somewhere in this direction. How do I throw the rock? The rock is in my hand, and currently, let's say I'm holding it stationary. I'm going to pull my muscles and accelerate the rock in a specific direction, and that way I'm going to speed up the rock while it is in contact with my hand. At a certain point, when I'm happy with the velocity, I'm going to slow down my hand, even by a little bit. The moment I'm going to start slow down my hand, the rock is going to lose contact with my hand surface. This is the important bit. At one point of my hand motion, I'm going to slow down my hand because I want to let go of the rock. The rock is going to lose contact with my hand. As long as I am pushing the rock in a certain direction by rotating my hand, let's say something like this, the rock is under the effect of gravity because weight is something that is always existence, and it is also under the effect of my hand's force. We are not calling this projectile motion. This is what we call forced motion, but not projectile motion because it's still under the effect of my force. The moment I let go of the rock and the rock starts its journey, let's say from my hand in this direction. So this is the point of time where I let go of the rock. From this point where it loses the contact of my hand, it is now only under the effect of gravity. So from this point, we can say that the projectile motion will get started. And let's say the initial velocity at which it leaves from my hand is u, where the angle it makes with the horizontal is, let's say, alpha, or maybe I can draw theta as well, doesn't matter. So this will be u cos theta, horizontal component, and the vertical component should be u sine theta. And from that point, the rock is going to travel up like a parabola. Why is it a parabola? I'm going to talk about this after a while. It moves on like that, where the horizontal motion is just basic normal unforced motion because there is no force working in the horizontal direction. For this entire motion, the force is always the gravitational force, which is the weight working on the object. So there is only force working downwards, which is the acceleration in the vertical axis, ay. Y in this case, subscript y represents vertical axis. So vertical acceleration should be minus g, working the downward direction, whereas acceleration in the horizontal direction, ax, should be 0. So the horizontal motion happens unobstructed or unforced. It's just inertial motion, and whereas the vertical motion of the stone would be under the effect of gravitational force. So and that way it's gonna cover this whole distance, and let's say after covering a significant distance, it will eventually hit the ground. Now, important bit, the motion is defined as a projectile motion till it hits the ground, or right up to the moment before it hits the ground. Because you have to understand, the instant it actually contacts the ground, it's gonna start applying some force on the ground, and by Newton's third law, the ground is gonna start to apply some force on the rock as well, which means the moment it touches the ground, it will suddenly start to experience two different forces. One is weight, which is the default one, and the new force is the reaction force from the ground. So the moment it hits the ground, we are not going to define this motion as a projectile motion. What is important for you to understand is that in many cases, we are asked that we are given certain variables. Let's say a certain projectile was thrown at this much velocity, we have this number at an angle of this much. With the horizontal, we have this angle as well. The question might ask us that what is the velocity, what is the final velocity of the projectile as it hits the ground? Many of us might feel like that whenever it will hit the ground, it will come to a stop, or it will penetrate into the mud or the soft thing, or it's going to bounce off. So it's going to have some velocity, something else that we might not be able to calculate. But that's not the point. Whenever the question tells you that what is the final velocity of the projectile when it hits the ground, it is actually asking you what is the final velocity at which the projectile hits the ground, which means what is the final velocity of the last instance of the projectile motion. So what is the velocity at which the projectile hit the ground? So the instance where the projectile is about to hit the ground, what was the final velocity? So what is the duration of the, what is the magnitude of the final velocity? And what is the duration of the final velocity with the horizontal maybe? So the final velocity of a projectile does not mean what happens after the bounce or what happens after the hit. It means what happens right before at the very instance right before it contacts the ground. এই পার্টটুকু বুঝা গেছে কিনা?
Sir, ওই অ্যাঙ্গেলটা কিভাবে আসলো স্যার?
Yes, sir.
এটা এই অ্যাঙ্গেলটা?
জি স্যার।
Well, the rock is going to rise up to a certain height because of the vertical velocity component that we have, because we have thrown it at some angle in the air and or in the atmosphere, or let's say in the space, because we're going to consider air is in zero. Because of the gravitational pull, the rock is going to start falling downwards as well. So eventually when it is going to hit the ground, it is going to hit the ground at some downward angle, right?
Yes sir.
So if I, other than me drawing, if I try to show you some projectile motion stuff, it can give you some pretty good idea what we are gonna handle here. Yeah, these are good components. We're gonna see about this figure of just after a while, but one of the things that I would like to show you is actually this. How big is this figure? Big enough. Open image in new tab, copy image, paste. Okay. Try to have a look at this figure, and this figure, I'm gonna help you understand this thing, so bear with me. Can you already see the arrows over here? Is it visible clearly?
Yes, sir.
Yes, sir.
There are violet arrows, which are the angled arrows. The orange arrows are only vertical. The blue arrows are only horizontal. In this case, they are trying to show us that what's going to happen for a projectile motion that is symmetrical. Symmetrical projectile means that it's going to be thrown off from this point and it's going to eventually land on the same horizontal level. So that's why theta equals to minus theta naught. I'm going to explain piece by piece. Try to understand. In this case, they are using theta 0. Theta 0 or theta naught basically means the value of theta at t equals to 0. The subscript 0 for a certain physical quantity means this is the initial value of that quantity. So at the instance when this object was actually thrown into the space, it was thrown with v0. We usually use the term u, but here they're using v0 for the velocity at time 0. Perfect, all right. And then the projectile is starting its motion. So this is the track the projectile is taking. This is the curved path the projectile is going to take. This blue arrow represents the horizontal component of the initial velocity. So this is v0, this is theta naught. So this is going to be defined as vx. And what is interesting, that for this entire motion, vx will remain unchanged. If you have a look at the length of all of these arrows, which is actually shown up over here once again, vx is the exact same no matter what. Because in the horizontal direction, there is no force. So there is no change of the horizontal component of the velocity. So I need you to visualize these two components of velocity, horizontal component and vertical component, individually differently. Look at these two things, which come from a single quantity, but try to consider these two variables independently of each other. So as the object is going to move, the horizontal velocity of the object is going to remain unchanged because it will be unaffected. Whereas the vertical component of the velocity is going to be affected by the gravitational force. So what happens? Have a look at the length of these vertical orange arrows. You can see as the object further rises further up, the length of this arrow is slowly becoming smaller, smaller, and smaller. And right over here, there is no orange arrow seen at all. This is the point of motion where the object has become reaches the object or the projectile has reached its maximum height. It means that it has come to a momentarily it is vertically at rest. What it means that it has just reached its maximum point of the rise and it is now about to fall down. So this is the point of the where vertical velocity has become 0. If you wonder why vertical velocity is becoming 0, the answer is very simple, because vertical velocity is affected by the negative acceleration of g. I wrote vertical acceleration equals to minus g. So g is basically eating up, or let's say reducing this orange arrow length at 9.8 meter per second. So every second passes by, the length of this arrow is reducing by 9.8 meter per second, and eventually it comes to 0 over here, and then as it further falls down, the arrow reverts its direction, because now the object is falling downwards, so the vertical velocity has now become downward, so it's going to fall downwards. And if it exactly falls at this point, then this vertical velocity component and this vertical velocity component should be exactly equal in magnitude, but only in the opposite direction, considering air resistance negligible, which is a default condition. So I might not mention it every single time, but bear in your mind that air resistance is considered negligible throughout our consideration for the scenario. But there are certain graphs where we're going to talk about the effect of air resistance, which is an additional part of the discussion. But for mathematical part or for the equation derivation part, we're going to consider air resistance 0 by default. Yes, Hassan.
স্যার আমরা যদি ভার্টিক্যাল ভেলোসিটিটাকে ভি নটটাকে ইউ ধরি আর যদি অ্যাক্সেলারেশন নেগেটিভ হয় তাহলে স্যার অটোমেটিকলি ভার্টিক্যাল ভেলোসিটি 0 হয়ে যায় স্যার
Yeah, but
উপরের পয়েন্টে জি স্যার
precisely, yeah, but it takes some time. After some time.
জি স্যার মানে সময় লাগে বাট লাইক ওইটা মাইনাস এই যে হাফ জিটি ওইটার সাথে চলে যায় স্যার
Exactly. So that's what happens for the duration when the particle reaches from the starting point to the highest point of the motion. But since it's not going to get stuck over here because inertia, because it's simply not going to remain in the space and remain there, it's going to start keep on falling further down. So that's why then the negative acceleration starts to add up towards the negative value of the final velocity for the vertical component, which means it starts to fall downwards. So it loses the vertical velocity in the positive direction for this much part, and then it gains the vertical velocity in the downward direction for the later falling part. So that's essentially what is shown over here for this part of the drawing. You can see over here that they're showing that slowly the vertical velocity is reducing. Just a second. Slowly the vertical velocity is reducing. It is eventually coming to 0. This is the positive vertical velocity segment, and then the vertical velocity is becoming negative, more and more negative, and eventually if it falls beyond the point, beyond the horizontal level of the throw, it can have a bigger vertical velocity magnitude compared to the starting value, because then it will have lost some actual GP because of the height difference. So that velocity can be slightly bigger. We're going to see about the calculation for these velocity components after a while, but I'll take questions from this discussion. Yes, go ahead.
Sir, the vertical velocity at the maximum point, it reduces because of gravity is pulling downwards, and it has no more force to pull it upwards. It is not because of any distance related things, right, sir? Hello?
Yeah, wait. The logic of your question is sound. It is not related to distance, it's related to force. But I'm going to correct your statement by a little bit. That I'm not going to say that the vertical velocity is reducing exactly at the top position. Rather, I'd prefer to word it in this way. As the object rises, the upward vertical velocity reduces for this whole duration, and it eventually becomes 0 at the highest position. So there is a gradual decrease of the vertical velocity, not a sudden decrease exactly at the topmost point. Do I make sense?
Yes, sir. But over here, distance does not play a role for the disappearance of the vertical velocity, right, sir?
No, distance is not the reason. Gravitational force or weight of the object is the reason.
And sir, over here at the bottom right corner, the downward component is maximum because kinetic energy is maximum at the lowest position, something like that theory, sir?
Yes, precisely, because the object happened to have gained some GP converted into K. So that K actually adds up to the vertical component, because the force is only working vertically. So all the additional velocity that you get is by virtue of the vertical component. That's why we have a bit bigger velocity here. In terms of energy conversion, yes, we can say there is high kinetic energy because of increased GP conversion. Yes.
স্যার ওই যে দুইটা পয়েন্টে এক্স অ্যাক্সিস কে কাট করে ওই দুইটা পয়েন্টে তো হাইট সেম না স্যার?
Yes.
From the ground.
Yes. One other point that is pretty important for us to understand, which I'm going to use this idea after a while, is that for all of the projectile motion scenarios, we always consider the throwing point or the launching point of the projectile as the 0, 0 point or the origin of our axis system, which means the farther it goes up in the upward direction, it has positive displacement. When it goes downwards, it has negative displacement, and if it's right, positive, and if it's left, it is negative. It almost projectiles are almost never drawn on the negative x-axis side, so we can disregard that fact. But the vertical sides are very important. This is the level that we consider to be the origin, which means as the object goes further up, let's say right over here, somewhere over here, it has a maximum vertical height of the whole motion, and as it falls further down, its vertical level slowly goes down, and this is the point where it has reached the same throwing level of the projectile. So it is at the same horizontal level. In cases, it can also fall further down. For example, if you are shooting a stone from the peak of a hill, or from the roof of a building, if you're throwing some projectile at some angle, it's going to eventually fall down beyond the horizontal level of our hand, because there is enough space for it to travel. So for those cases, this can happen. বুঝা গেছে?
Yes, sir. And sir, a few more questions, sir.
বলো।
Sir, although over here we are seeing a parabola, but can this, I mean, the real life situation be like we threw a ball and it just came back to our hand? I mean, vertically up and vertically down.
Yeah, that can also happen. That can also happen, which is basically a subset of the information that we have over here. For example, if we actually throw an object vertically upwards, in that case, that theta would become 90 degree. Theta would become 90 degrees. So if I just show it for this figure, maybe, let's say if your theta becomes 90 degree, what happens to u cos theta? So whatever the value of u is, u cos 90 basically gives you 0, right? So this would mean that there is no horizontal velocity involved. In that case, that would be a perfectly vertically thrown projectile. So this can, in that case, let me use a different color. It can work that it's going to go just vertically up, reach to maximum height, and then vertically fall down to the exact same point. That can also happen. In this case, the horizontal velocity is 0 for the whole scenario, because there is no horizontal component. We're only going to work with the vertical components. This is something that we call vertical projectiles. That can happen.
But sir, the graph won't change, right, sir?
Which graph?
I mean, the velocity time graph.
The velocity time graph for the vertical axis will be velocity time graph, or this, you have to understand, this is actually a distance versus time graph. So this is actually a coordinate graph. Here you can see this is the x coordinate, horizontal distance coordinate, and y over here is the vertical coordinate. This is actually y versus x. This is actually a Cartesian system, distance versus distance graph, vertical distance versus horizontal distance. So if you are looking at the projectile from the side, this is how it would look like at different time instances. Or if you, let's say, বুঝা গেছে, এটা কিন্তু টাইম বেস গ্রাফ না, এটার এক্সেসটা খেয়াল করো। যদি আমি টাইম বেস গ্রাফ আঁকি, তাহলে আমাদের গ্রাফটা ইভেন্চুয়ালি একটা শেপ নিবে। কি শেপ নিবে সেটা আমি পরে দেখাচ্ছি, একে দেখাবো। আচ্ছা, if we try to get some other information for the projectile motions, yeah, this is actually a really good image, although very small image.
তোর এই অ্যাঙ্গেলটা কিভাবে আসছে এটা একটু বুঝাবেন, একটু বুঝতেছি না।
কোনটা?
অ্যাঙ্গেলটা কিভাবে আসছে এখানে, থিটাটা, অ্যাঙ্গেল
এই অ্যাঙ্গেলটা?
জি স্যার।
এটা আসছে হচ্ছে this purple arrow or violet arrow that you can see. This is the final velocity. This angle is basically the angle between the horizontal component and the final velocity. Let me show you some animation, maybe that will help. Hold up. You have to understand, kids, you have to understand one thing. This is not the position of the ball for a duration of time. The ball actually travels over this whole curve. These are individual positions of the ball shown to us. The ball is not at all the positions at all the times. It is traveling like that. So this is something like a time-lapse video.
Sir, exam কি অত complicated question দিবে স্যার, like এত year related, like
Sir.
in depth?
Um, well, if teachers want to give you complicated questions, they can design a whole lot of complicated questions for you. That's the honest truth. But they usually don't, because setting up complicated questions is not a very ideal way to judge the students.
Sir, question.
Question বলো।
Sir, will the final, sir, we saw that there's a starting and the end velocity and of both vertical and horizontal. At the start and the end, are they the same? I mean, within the same length of travel?
With air resistance negligible for the same horizontal level, yes.
Okay, sir.
I said two things. Considering zero air resistance, which is the default case scenario, and for the same horizontal level, which means for this level, this motion and this motion are pretty much identical except for the duration of the vertical velocity component. So the length of this orange arrow and the length of this orange arrow should be exactly same, only there will be an opposite direction. And because these two lengths are exactly same, your theta should be also same. That's why they have written the theta equals to minus theta naught, because here the theta naught was shown as a positive acute angle. This angle is shown as a negative acute angle. Okay, Hassan, I'll try to take care of that information. কি দেখাইতেছিলাম জানো?
Sir, simulation. Yes, simulation.
অ্যাঙ্গেলটা কিভাবে আসছে ওইটার এক্সিস্টেন্স?
দেখাচ্ছি। ফিট সিমুলেশন তো লোড হইতে এত সময় লাগার কথা না। হোয়াট ইজ হ্যাপেনিং?
স্যার একটা কাজ করেন স্যার, আপনি ব্লেন্ডার ইনস্টল করে স্যার নিজের সিমুলেশন বানিয়ে ফেলেন। I mean, all that might take a bit of knowledge to make.
I like the idea. I might, but I'm not sure when.
Sir, you can even prepare for a lab using Blender, I guess.
আচ্ছা স্যার,
এটা কি এই অ্যানিমেশনটা অফ করে দিছে সোর্স থেকে নাকি কি করছে আল্লাহ জানে, আসতেছে না কেন? ফিটের
স্যার?
সিমুলেশন তো অনেক ভালো।
হ্যালো,
হ্যাঁ শুনতেছি, বলো।
ওই আপনার যে ফেসবুক আছে না, একটা ইন্সপায়ারিং কেমনে এই পোস্টটা আপনার কাছে জানতে চাইছিলাম আর কি।
আচ্ছা
লেটেস্ট পোস্ট।
ক্লাসে পরে বলি। Simulations are not loading. I don't know why. If it is, whether it is my internet connection or what it is. But I have used simulations in my earlier internet in my PC quite a lot. এই সাইটটাই কি আসতেছে না নাকি আল্লাহ জানে। আচ্ছা, anyway.
Sir, you can use multiple sites to check if they work.
This on Tutor Vista.
Projectile motion.
Okay. This part of the video might actually get a copyright issue, so I might actually discard this thing. I'll try to add up the link, so you can have a look at this thing. And 6:45 should work. দেখো আমি
Observe the athlete throwing a javelin. The javelin follows a curved path and lands on the surface of the earth. Such objects like javelin, which moves along a path determined by gravity and air resistance, are called projectiles. The path followed by a projectile is called trajectory. An object dropped from a height, an object thrown vertically upwards, and objects thrown obliquely upwards are examples of projectiles. In all these cases, the influence of air resistance is neglected. The velocity of the projectile varies from point to point. At each point, the velocity has components in the horizontal and vertical directions. The horizontal component of velocity remains unchanged throughout the flight. The vertical component of velocity continuously changes due to the force of gravity. Thus, the horizontal motion is a uniform motion, and the vertical motion is a uniformly accelerated motion. The magnitude of the vertical component is different at different points and is directed vertically downwards. Let us now analyze the motion of a projectile thrown obliquely. Let a body be projected from a point O with initial velocity VO. The projectile makes an angle theta with the horizontal axis. The velocity of the projectile at
Actually pause the video because I think this actually shows that how does this angle come into existence, because the angle of the angle that is shown in the figure that we have seen in the earlier case, for example, these are all angles of the final velocity or the instantaneous velocity of the projectile with the horizontal direction. So as the projectile rises up, this angle slowly becomes less. At the highest position, that angle is 0. As it falls downwards, that angle becomes negative because now it's a clockwise angle with the horizontal direction. So further it falls down, it gets a much bigger angle. Munaim, does that answer your question?
আমার কথা হলো আসছে কিভাবে না স্যার আনসার করে নাই
Acha, what is this angle? I mean, how do you define this angle, or what do you understand from the view of this angle? I mean, what is this angle?
ইয়েস
This is the angle that exists between the final velocity, or I can say instantaneous velocity of the projectile of that instant with the horizontal direction. So for this position, the velocity was working this way, and this is the horizontal direction. The angle between those two things is the initial angle. Here, that angle is gonna be, where's my pen? Here, that angle is this much. Here, that angle is this much. Here, that angle is this much. Here, the angle is 0 degree. Here, that angle is this much. Here, this angle is this much. So that's how the angle is produced. It is the angle drawn between the final velocity and the horizontal direction. The angle is actually not a physical thing that exists. An angle is a measurement that we do between two variables. I mean, if you look at the projectile, you cannot see these arrows or you cannot see this angle. The angle is something that we measure for individual different positions for doing the calculations. বুঝা গেছে?
জি স্যার বুঝতে পারছি
Beautiful. So that's that. And then আচ্ছা আমি আরেকটা জিনিস যেটা দেখা যাচ্ছিলাম সেটা হচ্ছে, দাঁড়াও,
স্যার আপনাকে একটা লিংক দিয়েছি, ওইটার সিমুলেশন মানে কাজ করবে স্যার, বিকজ ইটস ওয়ার্কিং এট মাই এন্ড।
কই দিছা?
আই মিন স্যার জুম চ্যাটে।
আচ্ছা দেখতেছি, হোল্ড আপ। Oh, beautiful. Thank you. Oh, this is nice. So,
স্যার you can also show the position vectors.
acha, position vector to project this. Where do I set fire? All right, beautiful. So if we increase that, so it is going stop, reset. Okay, so this actually has a pretty nice values. So we can throw it a bit upwards as well with two different velocities. And if we get rid of this factor, I think we can choose to angle. So initial velocity can be chosen to be larger. Launch angle can be set to be different values. And then if we fire and slowly go with the sort of time, so that's what happens. So you can see that the horizontal component Vx is remaining same. The Vy is slowly becoming 0, and then it start to reappear on the downward side, and can go on further like that and that and that. So that's basically what happens for the projectile. Here, one of the other things that they have shown that y0 equals to m equals to 0. So we can choose to set the projectile from an increased height if we want. For example, let's say if we want to shoot the projectile at 20, 0. So in that case, the projectile would be seen to fall beyond its thrown point. So you can have a much bigger vertical velocity component. For example, here you can see that the initial component have a height of about something, which you can set. This is, let's say, exactly 25, let's say, and this is, let's say, this is exactly 15. Can we say that 15? Yeah. So let's say these two components are perfectly set over here. I have chosen in this case to give the input for the initial vertical component and the initial horizontal component. And now if we allow it to move forward, exactly when the position vector is perfectly 0, for example, if I take that so you can actually see it whenever the Vy is almost 425, you're gonna have the same amount of height. So, and in this case also the y value is 20, which means whenever it has risen up by 20 meter and it has once again fallen down by 20 meter, you have nearly the same value of the vertical component of velocity. So that's basically how it works. Yeah, this is a good link. This is from ophysics.com. I'll try to remember that link and use this animation. There seems to be a lot of good animations over here. আচ্ছা, সো এইটুকু হচ্ছে আজকের ক্লাসের জন্য থাক। আমি নেক্সট ক্লাসে আমরা এই জিনিসগুলো ম্যাথমেটিক্যাল এক্সপ্রেশন নিয়ে কাজ করব। আর গ্রাফের একটা সার্টেন ভিডিও আছে, ওই ভিডিওটা আমি বের করতেছি, বের করে তোমাদেরকে আমি পাঠিয়ে দিব না, সো দ্যাট ইউ ক্যান অ্যাকচুয়ালি হেল্প উইথ ইট। শেষ পর্যন্ত এটা লোড হয়েছে।
তোরা দিকে শেষ করি ক্লাস।
হ্যাঁ, 9:30 তে ক্লাস শেষ। হ্যাঁ, we are going to finish the class right now.
বললাম যে এটা
হ্যাঁ, আমি ক্লাস শেষ করে দেখা সমস্যা নাই, যে অন্যান্য প্রবন্ধের 9:30 থেকে ক্লাস আছে, so that's why the class is finished. For those who want to leave, have to leave, you can leave, no big deal. Assalamu alaikum.
স্যার
Assalamu alaikum.